Is it okay?
Yes.
Can you see me or hear me in your Zoom?
And then it's only one thing. This is in Zoom.
Yes, yes. I already shared this. Yes. Can you hear me? You cannot hear. Okay,
Microphone.
please.
Sorry. Ever. Yeah.
Hello, can you hear me? So, okay, that's good. Okay. I can sit here. You.
No, it's okay for them.
Yes.
So we can let you face.
Yes. Okay. Start. Okay. Good afternoon, everybody. Today, I would like to introduce the basic principle of the processing of the XPS data, mainly by using CasaXPS. And we're gonna talk about how and what type of parameters you need to take into account when you are making a deconvolution of the peaks. And CasaXPS is a very powerful analysis technique for both spectral and imaging data. And that's basically you can process the XPS data and also the Auger data. I designed this course to be quite practical, so I'm not going to deep in a theoretical part or in a physical meaning of the each parameters. And since we have 1 hour, so I'm trying to be more practical in a way that we just introduce the most important and principles of the CasaXPS.
We cannot speak up because we don't have the.
Okay.
Let's speak loudly.
Okay. So first of all, if you have a XPS data, you need to make some first observation that you need to know what do we observe from a typical XPS data. And then here we just showing that how to make a quantification of data, mainly the atomic concentration, and also how to analyze the high resolution spectra, basically doing a peak fitting or create a deconvolution model. And also some important parameters you need to take into account when you are doing this high resolution. And here I am sharing a very typical survey spectra, which is in this case is for iron. As you can see, XPS gave us several peaks which located in a different binding energy, and each binding energy is specified for a specific atoms. So for instance, at 284.8, we have a carbon, and also we have hydrogen here, we have iron and other elements. The information that you can get from the survey spectra is the position of each peaks, and also you can calculate the atomic concentration by using the resistivity, relativity sensitive factor, and also the area of each peaks. So you can determine the atomic concentration of each element in the survey spectra. So the important features of XPS data, mainly with the high resolution, is that you need to take into account which peaks is related to the outer peaks. Outer peaks means that peaks that's related to the transition of an electrons from the outer shells to inner shells. And also you need to looking over the sharpness of the peaks, means that we know that this photoelectron created from the which area of the surface. If your peak is quite sharp, means that this information coming from the upper and outermost layer of the surface, a few nanometers, and also if you have some multiplet splitting on the peaks, means that there are some orbitals that are not completely filled with the electrons. For instance, in the case of chromium, you have the orbital of D with 3 electrons. Means that the first orbital is filled with 2 electrons, and the second one is half filled. Means that cause multiplet splitting. And also you need to take into account the shifting between the peaks. Means that this shift usually related to changing the oxidation states of the materials that you are working with. And also you need to taking into account the broadening of the peaks, which there are different phenomena that cause this broadening, like non-uniformities, also charging of the sample if you are dealing with non-conductive materials, and also energy uncertainty of the states. And also there is a schematics of the XPS, which is basically working based on photoelectric effects. So as I said, I am not going to into the details of the physicals and chemical meanings of the XPS data and how we can measure it. And here is the high resolution spectra related to the oxygens that's got on the iron alloys. As you can see, there are this peak can be treated with different oxides, different hydroxides, and on the surfaces. So also for each component, you need to define the constraint of the FWHM and also of the position of each peaks. So here we deconvoluted into the 4 peaks, and you basically need to take into account the most important parameter here is the FWHM, and for instance, for the oxides, you usually getting a thin FWHM compared to hydroxides, and also compared to the organic components. There are bunch of databases and literature basically on the internet, but this website of the XPS Simplified that belongs to Thermo Fisher, and also XPS Fitting that's from the Western University is quite reliable, and a lot of useful information related to different type of materials are present in this website. And also you can access to several tutorials, several informations, physical meaning, material science meaning on the CasaXPS software, and also it's related to the licensing of the surface and so on. So with this short introductions, I would like to go directly to the CASA software, and then we will be starting how to work with the parameters, with the options, toolbars, and all this stuff on the CASA software. So let me share the CASA software here. Okay. Yes, here we go. Here, I don't know if everybody installed the CASA on the system. You just need to install the demo version of the CASA, which is on the website. And here there are different toolbars. You can see here: file, view, window, options, select, and help. You just go to the view, and here you can select the tools that you are going to work with it. I need the tools. Also, I need the status bar, and also I need the options bar here, and also I need the SIMS bar. So we are going one by one to each option and see how we can use them. And here I need to, how can I minimize it? Yes, that's very good. Okay, here there are a part that you can, when you want to make a new working places in the CasaXPS, and here there is a part that you want to open the file that you are going to work with it, which I am going to select it on my laptop. And here you just find the XPS spectra. Also, you can change to the another one, yes. And here you can see that you have a XPS survey that make a calculation of each peaks and make a determining the atomic concentration. So I'm gonna delete all these parts, and then we are going to calculate the atomic concentration also on this optional example. Okay, so this first toolbars, they are related to the opening and saving the files, which I think they are not available for the demo version of the CasaXPS. But here there is a part that you can create the region here in the survey. And here also your library, which is most important part related to the survey spectra. Also, here is the part that you can process your spectra. For instance, if you are working with the polymers and non-conductive material, you need to first do the calibrations, because usually your peaks is shifted a few electron volts due to the charging of the surface. So we are here step by step. We are going forward how to process the XPS data. First of all, please.
The extract from the XPS at the lab, is it already in BMS format? We have converted.
You need to convert it. Yes, I will. We will get there. Yes. So here you need to make a calibration, and for the calibration, you basically need to select all your file, and you just say that all the files between 290 and 280, you need to calibrate them according to the 285. Means that you are calibrate them according to the adventitious carbon. So then if you go and select apply range calibration to all files, then you're receiving the file that you are going to add this condition. So if you put the OK, then you can see that if you then click on the peak, you see that my file is if you just zoom out on your here, you see that the file here become calibrated. So if I check my XPS, so I am going to delete all those previous process here, and then we're gonna start to reprocess this data and create this fitting model. Okay. Okay. So here you can see that the carbon peaks here, and then here also you need to redo the calibration, because I don't know why it is not saved in the previous one. You can again make a calibration quite directly. Just if you select here, the peak is 293, so you just put the calibration, and then it would be 284. If you check it again, let's show it to you that this is I don't know, this is, yes. Yeah. And then you can now start to treating your data. Also, there is another option here. You can just basically by selecting the data and zoom on each peak. And now with this reset options, which is here, just go back to the original display of the data, and then for each peak you can directly check it here, and then also you can make a smoothing of your data, which is here, according to the each baseline. Like if your peak is more Gaussian or Lorentzian, or if the combination between them, then you can avoid the noises, and by making the smoothing of this peak. For instance, if I put the smoothing of this peak, you see that's this noises completely removed from the surfaces. So but I'm not going to save these changes, because for now we are just testing each option of the survey. So let's go back to the survey spectra and also the library. So let's see that some of the peaks you don't know what type of elements it could be. Here, you have two options. One, for instance, selecting the peaks, and here it will suggest you which peak is likely it is. For instance, is it hafnium? Is it, I don't know, oxygen, Ph.D, any platinum or other type of the elements. But for as we know that peaks at 532, it might be oxygen. So we either select it from here, or you just go to the periodic table and just select the elements that you know might be on your surface. For instance, carbon, nitrogen, oxygen, iron, and also nickel, cobalt, and all the types of elements. You can just select them, and then you can here just select the find peaks. It will find it for you, and then create the region, and then you can clear here, and then it will automatically give us the atomic concentration. But usually the automatically it comes with a huge deviation. So me personally, I suggest to go do the calculation by each region. Then you can propagate your calculation to the other spectra. So the best way is that first to do the this calculation manually rather than automatically. So I'm gonna delete the scenes that the software calculated for me. So I will going to do this calculation by myself. So for doing the atomic, to calculating the atomic concentration, you need to push this bottom, quantify, and here, for each peak, you need to create a background and a baseline. For instance, just zoom out on this peak and just here push the bottom of create. Okay, so then you will come here and you are defining the start and the end of your peak. And then here you are inserting the type of atoms or elements that you are working with, which is in this case is C1's peak. And then the resistivity, the relativity sensitive factor for each element is defined according to the carbon as a reference. That's why the RSF for carbon is 1. And then for the other elements, we will see that all of them is defined as a just according to the carbon as a reference. So if you go to the next peak, which is oxygen here, and then you create your region, and you just basically need to left click and drag this line to the end of your peak and also to the start of your peak. And then you basically here inserting the information of your elements. Basically need to put just the element that you are working with, and just when you put the enter, you see the relativity sensitive factor will appear, and it will calculate the atomic concentration for you. And if you go to the next element, for instance, let's see that you don't know what type of element is that. So you have your database here, and you just select this one, select your element, and this software is going to suggest different options. Say that if your binding energy is around 705 electron volt, so it is PO for P3.5. And for instance, if it's 686 electron volt, it might be fluorine. So which is in this case is fluorine in this sample. So we are going to zoom out on that and then create another region for this peak and do this determining the start and end of the peaks, which could be here. And then you just need to insert the name of the elements. So, and then you see the relative sensitivity factor of the fluorine will appear here. And then for each peak, you can do this calculations, and which we are here getting more information. The more peak you are putting, the more information you got here. For instance, let's say to also to this peak, which is at 710. If you go to this peak, yes, here, yes. Okay. Yes. And if you just again create a region and you start from here and started from here, then it should be iron, which is Fd 2p. Then the relativity sensitivity factor for iron is 16.5. And you basically need to do all those calculation, and then the atomic concentration will be calculated. Then you have option here in the CASA for the annotation of your calculation on the data and the processing of data. If I delete the annotation history, so you see this information all will disappear. And here, if you just go to the annotation related to the region, you have all the possibility to the to what to present here and what not to present here. For instance, I said exclude the position, exclude the FWHM, or I want to keep the FWHM, and then I want to exclude the area. I want to include the standard deviation, also other parameters. So I will exclude I will exclude the name of the tag. Also, I don't need to include the RSF, and I don't need to include the background type as well. So also you can choose the font that you are going to use for the annotations, the style of this annotation, the size, and other properties of your samples. So you just click OK and just push the button apply, and then all those information will appear here. So this is the very basics about how to make a calculation related to atomic concentration, very basic parts. But of course, other options in the software. For instance, if I remove this history, and here, if let's say that I have two elements, so I will delete this one as well. Yes. And yeah. Okay. So here, yes. Here, let's say that I have made a calculation on the first spot, and I'm doing the annotation, and yes, yeah, and then I want to propagate my calculation to the next sample. You just need to select both of them, and here right click on your page, and you are choosing the which type of processing to be propagated. So I'm putting the region. I want to region to be propagate to the next sample. Also, I want to propagate the annotation to the next sample. And also, you can choose auto feed of the data according to the peak of the next sample, or remove this option and then do the fitting by yourself. If I put OK, yet here, unfortunately, the demo version will not give us this options to do it. So this was the very basic information you need to take into account for the calculation of the atomic concentration. But the most important thing and most accurate way to do this calculation is do it by region, as we did it here. Then you are making each region more precise compared to to doing it automatically by the software. But of course, this option will help to define if the sample of interest, or if those elements are presented on the surface of the sample or not. So this is the first part. Now, if we are going to the high resolution of of each peaks, for instance, oxygen and carbon, which are the two high resolution peaks that we are dealing with on our elements, and they are more often being used whether you are dealing with the conductive material or non-conductive materials. So for this one, let's see that you made the calibration and all those details, which we cannot do it here correctly. Now you can do the high resolution. So first of all, you need to create your region, which is you need to basically define the end and the start of your peak. So here I see that my peaks start from here. Also, it end up here. So then you need to define which type of background are you going to use. You can use the Togart, you can use the shearly and linear or non-linear backgrounds, but one which usually give us the most correct calculation is shearly. And if you just type the name of the shearly here and just put the enter, it will change to the shearly. And then after that, you just go here to the compound and create each peak's model that fits your high resolution spectra. Of course, for this part, you need to use a lot of databases, the one that we show it here, such as XPS. Yes. Yes. Here, if you go to the carbon peaks, you see that give us the some useful information for each element. For instance, with the adventitious carbon that give us that there are 3 peaks or 3 components related to the carbon peak. One is the carbon single bond with carbon, which usually located at 284.8, carbon single bond with oxygen, and the carbon again to 86, and the third carbon component located at 288.5. And also this give us more information related to the which type of material usually gives which type of components, and also there are some example of the fitting which give us some idea about the elements, and other useful information which can help when you are dealing with peak fitting and creating a deconvolution model. So here, the peak fitting for the polymers, PET, and there are other models related to the diamond-like carbon, related to the graphene oxide, and so on, and also on the metals. That's also show you when you are dealing with the metals, you have one peaks usually at 283, and also one peak at between 288 and 290. So this is the information that recommended to obtain before any peak fitting and deconvolution of the XPS spectrum. So let's go back to our model. So here, for making the each peaks, you need to just here push the create, and it's make a peak for you, and also you can select the create, and also you need to define the line shape of your peak as well, which here LA is related to the asymmetrical peaks, and the asymmetrical peaks usually occurs at the metals, and that's because of the interaction of the core atoms with the electron at the conduction bonds. So here, if I use the asymmetry, is not quite fitted. So if I go to the another type of the peak fittings, and here see here, yes. Yeah. Yes. Here, usually the first peak here, if you use the asymmetric spectra, you see here, and also you can see that our peaks is almost finished here, and then you can make another peaks, and you can just drag it to the end of to the position that you want. And here, for making the FWHM, you need to just manually enter the FWHM. And usually the first peak of the carbon should be quite thin. And what we saw in the software, that's fitted at 1.7, which is quite wide for this peak. So you need to use the thinner peak fit, such as 1.1. And also, if you go to the constraint and reduce it to 1.1 or less. And then here you need to, yes. And then if you just fit it, so it is not going to be bigger than this one. And also each peaks you need to make, and also here, each peaks related to the carbon, the FWHM should not exceed 1.2 or 1.4 maximum, the FWHM. So you just here put the 1.2, and for the constraint, you just put 1.2. And also, if you go to the next peak, you do the similar. Two, and then you see we are now we need to also make our region is spectra had a lot of noises, so we need to be quite careful with this also. Yes, and you see there is still one peak missing here. So if you put the create and create your peak here, and here also 1.2, and here you see you're getting fairly fitted spectra, but also, as you can see, there is one peak probably missed here, or it depends on your undersample, but you are getting fairly big spectra. But you need to take into account that your data are had a lot of noises, but this is the thing that you can get with this peak. And also you can define which peak do you have here. For instance, the first one is related to the carbon bonding with carbon, and also the second peak, which came here, is related to the carbon bonding with oxygen and carbon. And the third one, which is this is the fourth, so this is the third one, carbon bonding with the oxygen, and the last one, carbon bonding oxygen bonding with carbon, double bond with the oxygen. And here the same, you can make an annotation of the of each spectra, if I delete the previous one, you see, if you just select the components, here you can say that, for instance, I want to have the name of the tags, or I want to avoid it. Also, the constraints which we don't need it. The line shape here we don't need it, so we can exclude it. Also, you can either include or exclude the FWHM, also standard deviation, also include the other parameters here, also the ratio and the area percentage which we would like to have it. Also, you can include or exclude the position of each component, and also the RSF here, and also include the position of set, which we are not interested at this moment. So here it gives us the position of each peaks, and also the FWHM and the relativity sensitive factor and area of this peak, and also the standard deviation, because the reason why here putting 0 is because we didn't calculate the standard deviation here. If you put the standard deviation calculations, then you will have the yes. Then you will have the standard deviation here as well. So here one example related to the carbon peaks, and you can also do this deconvolution on the other peaks. So I would like to know if you now can install the CasaXPS on your devices and start to do this deconvolution on your computer. Of course, this is the demo version, but please.
484 for this 6 is the right number for the team.
The first. Yes, yeah, because we had the first time a problem at the calibration of the peaks, so that's why it's here. But yeah, that's correct. We have a problem with the calibration. I need to fix this part, and this version of the CASA, I never use it. I use the older version, and this is the demo version. I'm not quite satisfied with, and maybe this is the one of the options that we cannot use here. Also, this is the this materials is metals, and maybe it is not carbon. It's maybe you can designate it as a carbide or carbonate, as what we saw here. Yes, something 283 or something less than 284.8. If it's the binding is lower than that one, you will this usually related to the carbide peaks. Yeah. So you have it on your computer? Yes. So please, I will give you this. Please. Yes.
So for the density of the carbon is less than the one beside that, which is 285.21.
How do we know what?
Why not opposite side?
This is you are just using the simple fitting options in the software. That's it is not what you this is the usually the calculation of the software. Yes, the models that which makes more sense, but also you need to analyze other peaks as well. Then compare to them, you are like make your model. If, for instance, in the oxygen, you have more organic peaks, and then means that you have the peaks that's a lot of oxygen and carbon in it. So that makes sense if here the intensity of this peak, which is related to the carbon and oxygen, higher than the intensity of the peak related to carbon with the carbon. You know what I mean?
Know what we're supposed to see. Based on that, we are trying that.
What based on what? No, not the stuff that we expect to see. Based on the other peak modeling, based on the, for instance, here in this case, you need to also first make a calculation here. You see that we have a 12% of the oxygen. Okay, and here you also need to go to the oxygen peaks and see that, for instance, this peaks or the usually this one usually hydroxides, and also this one also sometimes organic components are located here as well. So means that when you have a some amount of this organic group, means that you have a carbon bonding with the oxygen. It's you need to also take into account this amount as well, not only the carbon. This is the make your deconvolution making sense. So you have it, yes? Okay. So let me. Okay.
And that was that's what I would. Yeah. How to convert it, I found it, but.
Better deconvolution. Oh, yes, please. Can you read the? I see, yes. So we need to go in. Just. You have your camera on this software? This demo version?
You transferred?
Yes, it's the source of this.
So for those ones joining us online, I thank you very much for your presence. And we thank Masoud for being here and giving us this amazing seminar on XPS deconvoluting using the CASA software. If anybody has any questions, I'm going to remain connected so you can, if you have your software installed and you want to, you have some samples that you want to try and use, you can go ahead and ask your questions. Okay. And you can ask through the chat, or you can open your microphones. If not, you're free to go. Thank you very much.
Send it to this flash drive.